In module 2 of chapter 2, we shall discuss the Lagrange's equation of motion of first kind and the related matters. So far, we have found that the constant forces are not known to us. As a result, it creates some problem in solving Newton's equations of motion. Newton's equation of motion is basically a relation between the total force and the acquired acceleration. So, if the force of constants are unknown to us, then how one can solve Newton's equations of motion? As a result, we have to find some other way to solve such problem. In this module, we shall obtain Lagrange's equation of motion of first kind. First of all, we shall discuss about the problem associated with the constraint forces. We have discussed the detail about the constraint forces in previous module, that is module 1 of chapter 2. Now we shall discuss the problem related with the constraint forces. Then, to overcome this situation, we shall derive the Lagrange's equation of motion of first kind. Later on, we shall define virtual work and will obtain the principle of virtual work. We know that the total force in a dynamical system which is under some restrictions is the sum of the externally applied force and the force of constants. We know that the restrictions or constants are caused by some forces which are known as force of constants or constraint forces. In previous module, we came to know that the forces of constants are unknown in nature. So, one cannot calculate the total force, which is the sum of applied force and the force of constants. As a result, some problem arises because Newton's laws of motion, particularly second law of motion, is basically a relation between the applied force and the acquired acceleration. If one is unable to calculate the total force, then he or she cannot solve Newton's equation of motion. This is the main problem in such cases. To overcome this situation, let us consider the motion of a particle having mass m under the velocity dependent constant given by g, which is a function of r vector dot time t equal to 0. R vector is the positional vector, whereas r vector dot gives the velocity vector, t being the time. As the constant relation depends on velocity r vector dot, so it is non-holonomic in nature. Total force acting on the particle is given by capital F vector, which is equal to F vector superscript A plus small f vector, where F vector superscript A is the applied force, small a stands for applied force, whereas small f vector is the force of constant. Now, Newton's equation of motion becomes small m into r vector double dot, which gives mass into acceleration, is equal to total force, that is capital F vector. If we substitute this relation here, we get equation 2.2. The number of equations are 4. Equation 2.2 gives one equation, whereas 2.1 gives 3. Here R has 3 components, so we get 3 equations from 2.1. So we have total 4 equations in this case. Whereas the number of unknowns are 6. 3 components for unknown constant forces and 3 components of R vector. So number of unknowns are 6, whereas number of equations are 4. Therefore, one cannot get unique solution. As a result, the problem does not possess unique solution. For unique solution, we have to provide some additional constraint relations. The main problem of dynamics is to obtain the total force or to eliminate them from the given relation. In these cases, we have to know all the necessary conditions required for this. This leads to obtain the Lagrange's equation of motion of first kind. To obtain Lagrange's equation of motion of first kind, let us discuss about 2 types of constant. One is bilateral constant and another is unilateral constant. First of all, consider the bilateral constant. In case of bilateral constant, at every point on the surface, both the forward as well as backward motions are possible. General form of such constant is given by f function of r vector dot t equal to 0. This indicates that this constant is bilateral. In case of bilateral constant, we have mentioned that forward and backward motions are possible. So we have the relation with greater or equal to as well as less or equal to sign, which finally gives equality sign. On the other hand, in case of unilateral constant, forward motion is not possible at a particular point on the constraint surface. As a result, only the backward motion is possible. So, general form of such type of constraint is given by small f function of r vector dot comma t greater or equal to 0. R gives the positional vector, r vector dot is the velocity, t is the time. Now let us derive Lagrange's equation of motion of first kind. First of all, consider a holonomic bilateral constant given by g function of r vector t equal to 0. Please note that this constant relation is independent of velocity r vector dot. So, this constant is holonomic. It is an equation, so bilateral. Let us calculate the time derivative of 2.3. This gives del del t of g plus del del r of g into r vector dot. Here we have used the chain rule of differentiation. This dot indicates that we are taking the dot product or scalar product of 2 vector quantities, which are del g del r vector and r vector dot. R vector dot is the velocity, that is ddt of r vector. If we again differentiate it with respect to time t, we get equation 2.5. From this relation, one can easily find that the acceleration r vector double dot is directly affected by the term del g del r vector. There are no acceleration term in these three terms. As force is directly proportional to acceleration, so force is also directly affected by del g del r vector. Because of the scalar nature of this term, we can comment like this. Therefore, F vector must be parallel to del g del r vector. Thus, F vector equal to lambda into del g del r vector. Lambda is a scalar quantity which is the constant of proportionality. Here we have considered the holonomic bilateral constant. Now let us consider non-holonomic bilateral constant of the form g function of r vector dot t equal to 0. In a similar manner, let us calculate the time derivative of this. We get this result. Here also the acceleration r vector double dot is directly affected by del g del r vector dot. Please note it. So, F vector can be written like this. Lambda is a scalar. In case of holonomic constant, the constant relation is given, or in case of non-holonomic constant, the constant relation is given. That is, we know this condition that has been provided. Therefore, F vector is known except for lambda, because lambda is unknown to us. Now, there are 4 unknowns. One is lambda and 3 comes from r vector, components of r vector. And there are 4 independent equations. 3 equations from here and 1 equation from here or from here. That is, we have 4 equations and 4 unknowns here. So, unique solution can be obtained. Therefore, F vector can be uniquely specified along with lambda. Lambda is known as Lagrange's multiplier. Newton's equations of motion, which is basically a law connecting the acquired acceleration with the total force, now becomes like this. This is the mass into acceleration force and this is the total force. This term gives the applied force, whereas the constant force now becomes this one. Replacing this, we get the modified form of Newton's equations of motion. This is applicable only for holonomic one particle system. You can find it from this relation, that is the constant relation is independent of velocity r vector dot, so it is applicable for holonomic system. Similarly, for non-holonomic system, Newton's equations of motion become like this. We have already mentioned that lambda is known as Lagrange's multiplier. Here we have considered the one particle system. Next, consider the motion of a system of capital N particles having k bilateral constraints. Constraint means some imposed restrictions on the dynamical system. Please note that k must be less than capital N. Bilateral constraint means on the constraint surface both forward as well as backward motions are possible. Let us consider the holonomic bilateral constant, which is of the form like this: g suffix I function of r vector t equal to 0, I varying from 1, 2 and so on k. For non-holonomic system, we have the constants which are of the form g suffix I function of r vector dot and time t equal to 0. Now, Lagrange's equations of motion of the first kind for the jth particle become m suffix j into r vector double dot suffix j minus f vector suffix j superscript a minus summation over I equal to 1 to k lambda suffix I del del rj vector operated on g suffix I function of r vector suffix j t equal to 0. Here we have used only the summation to obtain the Lagrange's equations of motion of first kind for the jth particle. These equations are valid for j equal to 1, 2 and so on capital N. Rj vector double dot is the acceleration of the jth particle whose mass is m suffix j. F vector suffix j superscript a gives the applied force on the jth particle. Lambda I are the Lagrange's multipliers. Gi are the constant relations. T is the time. For non-holonomic system, we have such type of equations. This differs from this equation here. Here the constant relation depends on velocity explicitly, whereas here the constant relation does not depend on velocity. This is holonomic, this is non-holonomic. We have already mentioned that F vector suffix j superscript a are the total externally applied force on the jth particle of the dynamical system we are considering. Here total number of scalar equations is 3 into capital N plus k. We have already mentioned that we have capital N number of particles, so Rj varies from 1, 2 up to capital N. Each Rj has 3 components, so we have 3 into capital N, and k is the number of constant relations, so we have 3n plus k equations, whereas the number of unknowns are 3n plus k So, unique solution is possible. Please keep in mind that these equations are coupled. So, obtaining solutions of these equations become very complicated. So, it is of little help. But if one can solve it, it gives accurate result which are very helpful to us to overcome the situations in case of constant motion where the constant forces are unknown and we are unable to form the equation of motion using Newton's laws of motion. Let us discuss the principle of virtual work. An imaginary displacement which is consistent with the constant relation at a given time is called virtual displacement. The term consistent with the constant relation means we have to follow the constant relation, that is, the constant relation will not change during the motion. In such cases, we have to disallow the time, that is, we have to freeze the real time. This is quite ambiguous and is not possible in real life. We have displacement, but time will not change. This is rather a fishy situation. That is why we have used imaginary. A finite displacement dr vector takes some time dt to occur. For virtual displacement, one has to disallow the real time to change. That is, dt will be 0, but dr non-zero. Lagrange first introduced the symbol delta r vector to denote the virtual displacement, and this is represented by delta r vector is equal to dr vector when dt equal to 0, that is, time does not change. This is the basic difference between the ordinary displacement and virtual displacement. To denote virtual displacement, we use the delta symbol. Let us define virtual work. Virtual work done by the force capital F vector due to virtual displacement delta r vector is delta W equal to F vector dot delta r vector. We know that work done is defined as force into displacement. Here we are considering the virtual work, so we have to consider the virtual displacement. F vector dot delta r vector is the dot product of two vector quantities F vector and virtual displacement delta r vector. In static equilibrium, there will be no force, that is, F vector vanishes. As a result, sum of externally applied force and force of constant also vanishes. Substituting this here, we get delta W equal to 0. That is, we have F vector superscript A dot delta r vector plus F vector dot delta r vector equal to 0. Here dot means we are taking the dot product or scalar product between two vector quantities. If we assume that virtual work done by the constraint forces vanishes, then we have F vector dot delta r vector equal to 0. Substituting this, we get F vector superscript A dot delta r vector equal to 0. For a system of n particles, we have delta W superscript A. This is used to denote the virtual work done by the externally applied force equal to summation over I equal to 1 to small n Fi vector superscript A dot delta Ri vector equal to 0. Thus, the necessary condition for static equilibrium is that the virtual work done by the applied forces should vanish, provided the virtual work done by the constraint forces vanishes. This is the principle of virtual work. The systems for which virtual work done by the constraint forces vanishes are known as D'Alembertian systems. In this module, we have discussed the constant forces and related problems in connection with the constant motion of a system of particles and how to tackle such problems. As a result, we have obtained the Lagrange's equation of motion of first kind, and also the drawbacks of such equation has also been discussed.